So in this video, we're going to look at example 2 and continue on with our notes. This is on page 7. So we're going to go and prove these identities, but first, before we can prove them, we have to look at the non-permissible values. So the non-permissible values, again, are values in which the function is not defined or does not exist. So for example, in the first one, for A, we have a problem where secant is, because it cannot be 0. So we know that secant, theta, cannot be 0. Or in other words, I know that 1 over cos cannot be 0. Well, 1 over cos cannot be 0 in general, but I'll still have a problem when cos theta is 0. And when is cos theta 0 again? If you think about our unit circle, at pi over 2 and at negative 3 pi over 2, our coordinates for our unit circle points is 0, 1, and 0, negative 1. So if you remember from the last unit, cos at pi over 2 would be 0 because the first coordinate, the x coordinate, represents our cos value. That means theta cannot be pi over 2 and 3 pi over 2. Or in other words, if I want a general solution for all of the places that cos would be 0, that means that theta cannot be pi over 2 plus some k pi. Notice it's not 2 pi because then I'll be missing this 3 pi over 2. If I did plus 2k pi. So that's why I'm doing plus k pi to include the 3 pi over 2. And this is where k is the element of the reals. The other problem is for cotangent. Remember cotangents? That is cos theta over sine theta. That means I also have a problem when sine theta is 0. So sine theta cannot be 0. That happens at 0 and pi. Because now it's my y coordinate that I look for to get my sine value here. So theta cannot be 0 and pi. Or if you want to include all of them, then it would be theta cannot be pi plus k pi for k in the element of the integers. And that's it for that. Now we can prove it for all theta values. If you just look at the left-hand side, we can simplify this, or we can also simplify it from the right-hand side as well. In the end, one will be easier than the other, for the most part. So let's start with the complex side first, and looks like the cotangent sine and secant one would be the complex side, so we can start off with that. So that's my right-hand side, which is cotangent theta, sine theta, all over secant theta. Well, I probably want to change the cotangent and the secant. As I've said probably before, the ones that you want to change are generally the ones that are not our regular trig functions. So sine, cos, those are the two that we'll commonly see. And even tan, we can break that down to sine over cos. So in this case, I'm going to take my cotangent and replace it with cos theta over sine theta. So that's its equivalent. Now I'm going to leave sine theta alone here. And then in my denominator, that'll be 1 over cos. My sines will cancel out at the top. So then I'm left with cos theta over 1 cos theta. If I bring it back up, this is going to be cos squared theta. And that's my left-hand side, so I'm done. I proved the left-hand side is equal to the right-hand side. You could have also done it with the left-hand side. You probably have to do more work though. So it's better to start with the complex side and then simplify it to make it look smaller. For part B, I'm just going to erase this out of some room here. Now we have a sine theta plus tan theta over 1 plus cos theta. My problem is right here. And I also have a problem for secant because that's also 1 over cos theta. One plus cos theta cannot be 0 from my fraction, which means cos theta cannot be minus 1 if I subtract 1 on both sides. So when does this occur? This occurs at pi. And if I want to include all of them, then I would say pi plus 2k pi, where k is the element of the integers. That's one permissible value. The other one occurs here at 1 over cos, and this implies that cos theta cannot be 0. And cos theta is 0, as I said before, at pi over 2 and at 3 pi over 2, but we want the general solution, so I'm just going to add k pi to that, and then it'll include all of them. So those are the two non-permissible values for our identity. And this one, we're going to have to simplify both sides to prove it. So sometimes we can't just prove the left-hand side and get the right-hand side and vice versa. We need to simplify both sides and eventually we'll have something in common. Let's look at the left-hand side first. Okay, so for this one, what I can do is break down that tan theta to sine over cos. And then I'm going to simplify my numerator more by putting it under one common denominator of cos theta. That means I need to multiply the sine here by cos theta, top and bottom. So I have sine theta, cos theta, plus sine theta, all over cos theta. And then this is all over 1 plus cos theta. Just move up here. Now I'm going to factor out the sine theta at the top, which leaves me cos theta plus 1, all over cos theta, and all of this is over 1 plus cos theta. These cos theta plus 1s can cancel out, so I'm just left with sine over cos. And that is also equal to tan. So it looks like this is where I just end up after I simplify everything. And that's not exactly what I wanted, because I want sine theta, secant theta. So now this is where I'm going to go to the right-hand side to see if I can get sine theta then. Then the right-hand side will be equal to the left-hand side. So my left-hand side is sine theta sec theta. I'm going to change the sec theta to 1 over cos. So that means I have cos on the bottom, and look at that, there's our tan. So because when we simplified the left-hand side, we got tan theta, and the right-hand side, when we simplified it, we also got tan theta, then the left-hand side equals the right-hand side, and then we're done. And that's it for that.